trying to figure this thing out. Okay, I can see everyone now.
Well, we have 3 chairs, so between the 3 of you, hopefully you can see everyone. So, hi Ramanjam, you're also here, right? Jam.
Yeah, so we are live on YouTube and the session is all yours.
Hi. The first talk of the session would be by Pratyay Mukherjee from Visa Research. He'll be talking about adaptively secure threshold symmetric encryption.
Okay, thank you, Shashank. There is some, should I talk? Okay. So, okay, I'm going to talk about adaptively secure threshold symmetric encryption. And this is a short presentation and the full presentation is available on YouTube. So the story starts from a very basic question that how to store sensitive data. If you Google that, immediately the best answer pops up that encrypt your data, which is great. However, it's slightly more detail. What's happening here is that basically it reduces the storage requirement from big data to small keys. So earlier you had a lot of data to securely store somewhere. Now you encrypted it. That's great, but now you need to store the key. So we are going to talk about how to store the key in this talk. So there is a naive approach where you can store the secret key in one server and the ciphertext in another, keep them separated. However, that becomes a single point of failure because if the adversary breaches into the server where the secret key is stored, it can basically decrypt all ciphertext that ever been encrypted with the secret key. So typically in industry, what happens is that they use hardware security module or HSMs to store the secret key and use whenever you want to decrypt, use the HSM, call the HSM to do the decryption. There are several issues with the HSMS solution. First of all, there is trust issues like there are side channel attacks. Then there is a lack of flexibility because HSMs are kind of attached to very specific programs. So it's kind of hard to change or update the encryption algorithm. And then there is a high cost of good HSM. As you can see that the cost can vary from $40 to several hundred thousand. So there are also software-only solutions that does not involve any hardware-based solution, and we are going to focus on that here. And one of them is offered by these services like Vault, where secret key is stored among different servers in a secret shared manner. And then while decrypting, during decryption, the secret key is gathered in one server and then decryption takes place. The problem with this solution is that since secret key is reconstructed in one server, it's vulnerable to so-called snapshot attacks, where adversary can breach into the system during the decryption and can capture the secret key. So we want software-only solution, but without any reconstruction. And the obvious question that comes up, like to use general MPC. And there are actually line of works that does this generic MPC, where basically instead of reconstructing, they use this particular decryption function without reconstruction and output the plain text. The good thing about using this kind of approach is that it can compute any scheme because general MPC basically can compute any functions. For example, AES, which is a standardized encryption scheme, and that's how it can comply to the standards. A bunch of problems of this solution is that it's not scalable. It's either highly interactive, that there are a lot of rounds of communications involved, or highly inefficient. If it is round optimal, then it becomes kind of inefficient. It's also bandwidth intensive because parties talk to each other and the communication is like order of n square. And it uses the particular circuit as a non-black box manner. Like first you need to convert AES to a Boolean circuit, and then you can use MPC. So there are basically huge efficiency issues. So in 2018, I, along with Shashank, Payman, and Peter, proposed this solution called distributed symmetric encryption, or DICE. And in that paper, we actually did formally defined threshold symmetric encryption with guarantees like privacy and authenticity for up to T malicious corruptions. It's a generic construction based on any distributed pseudo-random function with properties like round optimality and order of n communications. And there are also several efficient implementations. So in this paper, so one problem with this solution is that it's only secure against static corruption. When the adversary corrupts the parties in a static manner that stays the same throughout the game. So in this work, we actually updated that to adaptive setting. So in particular, we formally defined adaptive threshold encryption with the same privacy and authenticity guarantees. This solution with the construction, the generic construction that was in DICE actually becomes adaptive secure when plugged into with an adaptively secure DPRF in a black box manner. And we propose an instantiation of an augmented version of Naur, Pincus, Rheingold DDH-based DPRF that was also used in DICE using ideas from Liebe, Joe, and Jung. Their work actually did for adaptive threshold signature. The idea we borrowed and we plugged in to augment a distributed PRF in the adaptive setting. So I do not have a lot of time to discuss the details. So let me just briefly talk about what is adaptive and static security. In static security, basically, parties are corrupt in the beginning of the execution, and this just stays the same. Whereas in the adaptive setting, parties can corrupt at any time of the execution. For example, it can gather some knowledge and then can decide to corrupt other parties. Let me briefly talk about the DDH-based DPRF and our augmentation. So NPR's DDH-based DPRF is kind of a simple solution where you use a hash function to the input and raise to the power of k, where k is secret shared among different parties. Now here actually the problem with this solution is that when in the proof you need to use the key as a DDH unknown value, that variable. So for that particular problem, it's kind of important that corrupt set is known. So it's not really adaptively secure. So in adaptive security, it's the change is very simple. Instead of using one key, we use two keys like U and V. It has two parts. And the DPRF construction becomes HX to the U times GX to the V. So basically the other part stays basically the same. So the main idea is basically reduction always knows the key K and hence can give correct key share for adaptive corruption. So whenever the corrupt query happens, it basically can give out the particular key. And via random oracle programming, adversary does not have enough information about K. So that's an information theoretic argument. So let's look into the difference between static DPRF and adaptive DPRF. So in static DPRF, the construction is like HX to the K, which is equal to G to the RK. Whereas the adaptive DPRF, it can be written as G to the RU plus SV. And with using DDH, we can switch to a hybrid where it's like G to the R times U plus S prime V. And an unbounded adversary gets information like R1, R2, and R1 times U plus S prime V, R2 times U plus S prime V, and so on. So S primes is the same. That's actually the main trick here. And that's how it kind of behaves like in universal hash functions, as the proof is kind of similar to the hash proof system. And basically, information theoretically, K has enough entropy given adversarial view. So that's basically the trick here. So the other DPRF construction, which was PRF based, actually we observed that that's actually already optimally secure if we use a simple guessing technique where the reduction can just guess the corrupt set. And the blow up is of course is at the order of n choose t, but as we see that this solution already has efficiency that scales with n choose t, so it basically adds another constant factor. So with that, I summarize the contribution. So we defined and constructed adaptive threshold symmetric encryption and instantiated with new adaptive construction. And the slowdown is only 2x, which is a decent price to pay for a better security. The adaptive DPRF proof is conceptually much simpler than the static one. And we are in the paper, actually, we also provide a stronger adaptive TAC version. And for that, we propose a simple NISIC proof for a specific commit and proof statement in random oracle model. So as a future work, one can think about removing random oracle without compromising efficiency. So thank you. I'm ready to take any question if you have.
Yeah, it seems unfortunately we don't have time for questions at this moment. We'll just jump right into the second talk. If the speaker can please. Yeah.
And Pratya, I would request you to just look at the chat, and if there are any questions, you can answer it. As of now, I don't see any questions.
Okay, sure, yeah.
So do you see my slides now?
Yes, I can see them.
Okay, good. Okay, so this is the brief presentation of vetted encryption, which is collaboration with Martijn Stam. So the intuition of vetted encryption is that a recipient gets to specify which senders actually gets to send them encrypted messages by setting up a public filter. And a sender is vetted by being given a special encryption key that they use to encrypt messages. And they send the ciphertext to the filter, and if the filter verifies that the sender is actually vetted, then the message is forwarded to the recipient, and if not, the message is rejected. So we have two different versions: the identifiable vetted encryption, which is the case where the filter knows the identity of the sender, and opaque vetted encryption, where the filter doesn't know the identity of the sender. And we can start off with IVE, which has 5 algorithms. The key generation outputs a public key as well as a secret key. The secret key is used for deriving encryption keys of users or senders, and also decrypting messages. So here note that the identity is actually given as input to both the verification algorithm as well as the decryption algorithm. And we define integrity as the advantage of the adversary winning the game given here. So the adversary is given the public key, and she also has access to a corruption oracle that gives her encryption keys of users, as well as an encryption oracle, as well as a decryption oracle. And the adversary should output a ciphertext which hasn't been given to her by the encryption oracle, and which verifies under a uncorrupted identity. And this captures the notion that only vetted senders should be able to pass the filter. We also have confidentiality, which is reminiscent of indistinguishability for public key encryption schemes. So here the adversary gets the public key of the scheme as well as access to a derivation oracle. And here she can specify identities, encryption keys, as well as to messages M0, M1, but she's not able to distinguish between encryptions of neither M0 or M1. So to construct an IVE, we require a unique identity-based signature scheme, and we achieve this by applying the known de-randomization certificate-based transformation to a unique signature scheme so that we get an identity-based signature scheme. And we require of this that it achieves outsider unicity, where the adversary gets the verification key and also has access to a derivation oracle. And the hardness is that the adversary shouldn't be able to output 2 distinct signatures that verify on the identity and message. And given this primitive, then we can construct an IVE, which is a encrypt and sign construction with the public key encryption scheme, as well as a unique identity-based signature scheme. And then the security of this construction follows from the properties of the building blocks. Then we can move on to OVE, where the structure is similar, but here the key generation outputs an issuing key and a decryption key, as well as the public key. So the issuing key is to derive encryption keys of users, and the decryption key is to decrypt messages. And here the identity isn't an input to decryption, but an output. So here we also have the notion of integrity, where the adversary gets all the keys, but shouldn't be able to output a ciphertext which verifies, but opens to an invalid message or identity, as this would allow spamming of a recipient. We also have the notion of privacy, which encapsulates both anonymity and confidentiality. So here the adversary gets the public key and issuing key, and she's able to query an encryption oracle with tuples of encryption keys and messages, but she shouldn't be able to distinguish between encryptions of those tuples, so that the ciphertext doesn't leak any information about the message nor of the identity of the sender. And finally, we have traceability, where the adversary gets the public key, corruption oracle, encryption oracle, and decryption oracle, but she's not able to output a ciphertext which verifies, isn't forwarded to her by the encryption oracle, and opens to an uncorrupted identity. So an adversary shouldn't be able to construct a ciphertext which opens to an identity for which it doesn't have an encryption key. So our construction for OVE is a verifiably encrypted certificate, which is similar to the sign, encrypt, and proof construction for group signatures, but ours is somewhat simplified. So here the certificate is actually the encryption key of the sender. And to encrypt, we construct a ciphertext using the message, certificate, and identity and randomness, and then construct a proof that the sender actually knows all the components that go into the ciphertext. And here again, the security follows quite easily from the properties of the underlying building blocks. So to conclude, we present a new primitive, vetted encryptions, and 2 versions of this. And because of the careful construction of the primitive and the security notions, we can relax some of the requirements of the building blocks that we use. So for example, only requiring outsider unicity of the signature scheme used to construct an IBE. So the full version is on ePrint and contains all the details, as well as security proofs and discussions and comparisons with other primitives, so group signatures and sign encryption, for example. But for now, I'm happy to take any questions that arise.
Thank you. We have about 3 minutes for questions.
Yep.
Are there any questions?
So maybe I could ask one. So you're using general NISIC proofs, or is it like tailor-made for specific constructions?
Sorry, could you repeat, please?
So in your construction, do you use generic tools like when you say NISIC and NIZK proofs?
Yes, we use a quasi-adaptive NISC for the OVE construction, where the CRS depends on the parameters of the language.
Okay, and this is for NP language and NISIC for all NP languages, or do you have specific constructions for your?
So the language that we define for the quasi-adaptive NISC is the ciphertext which verify, or the valid ciphertext, if you will. I don't know if that answers your question.
My question was, is it based on specific assumptions, or is it for a specific construction, or is it a generic thing?
I believe it's in the random oracle model, but other than that, we don't really go into specifics.
Okay.
Have you tried implementing your vetted encryption scheme?
No, so far this is just a suggestion for a sort of generic construction. So that would be future work, and as well as making it sort of dynamic so that you can add users but also remove them. So far we only add users continuously but can't remove them.
Thank you. Any other questions? Do we have any questions on the chat thing?
No. And none on Zulip also, I suppose.
Okay, then I guess we can move on to the third talk of the session. Thank you.
Can you see my screen?
Yes, I
Yes.
can.
Okay.
Yeah, the third and last talk of the session, is by Julian Kramer and Patrick Strook. Sorry if I am mispronouncing anything. It's on security of public key encryption against resetting attacks.
Right. Yeah, thank you for the introduction. Yeah, in this work, we are looking into resetting attacks, which were proposed by YILEC in 2010. And this is a strengthening of the standard in CPA security notion for a scenario where we might reuse the randomness used during encryption. And so the scenario would be if we run an encryption scheme on a virtual machine where we derive the randomness from some security critical state. And due to the possibility of snapshots for the virtual machine, it might be like that we later restore such a security critical state and then use the same randomness. Now, in this security game, the adversary gets some target public key, PK star. Then similar to the NCPA game, it has some challenge oracle where it can send 2 messages and then get the encryption of either the left or the right message. But the crucial difference here is that now this randomness R star here is fixed, and this is chosen initially at the beginning of the game and then fixed throughout the game. So every encryption will always be under this randomness. Then in addition to this challenge oracle, the adversary also gets a learning oracle where it can specify a public key and a message, and then gets the encryption of the message under the public key, again using this fixed randomness R star. And in the end, we have the same that the adversary has to guess the bit B of the challenge oracle. But there are some inherent limitations or some queries which we have to forbid in order to make this a meaningful security notion. So for instance, the adversary is not allowed to query the challenge oracle on 2 queries which agree on one of the messages but disagree on the others, because essentially the part is deterministic. So in the left case, it would be the same ciphertext, and in the right case would be 2 different ciphertexts. And also the adversary is not allowed to ask a message to a learning oracle, which it already asked to the challenge oracle. Now the claim made in this paper is the standard one for NCPA security, that we can only focus, or we can focus on an adversary making only a single query to the challenge oracle, and this implies security against adversaries making multiple queries. So essentially, the adversary tries to distinguish between the 2 cases where the oracle is instantiated with the bit 0 and with the bit 1. And then Jilek proposed several hybrid games, GI, where in game GI, the first I queries are answered by encrypting the right message, and the remaining queries by encrypting the left message. So this means that the game G0 corresponds to the oracle here on the left and GQ to the oracle on the right. And then he proposed to use a hybrid argument over these games in order to show the simplification of the notion. However, this was then in 2014 identified as flawed by Patterson, Schuld, and Seborn, who showed that this results in a forbidden query by the reduction. Now in this work, we further investigate this issue of the proof. And for this, we define 2 types of special queries, first, which are allowed in this game. First one is the flipping query, where just after making query M0, M1, the adversary later queries M1, M0, and repeating queries where the adversary just makes the same query twice to the challenge oracle. And for these, we essentially show that these consecutive hybrid games from the hybrid argument of the proof, these queries allow to distinguish these games almost perfectly. So we cannot prove the statement using these hybrid games, actually. We then look into how we can nevertheless prove the claim. And for this, we do 2 changes in the proof. The first one, instead of using just a single hybrid argument, we use 2 hybrid arguments. This solves the problem we have with the flipping queries. And the second one, instead of doing each of the hybrid arguments over the number of queries, we only do it over the number of non-repeating queries by the adversary. Now here we have again the picture, the adversary trying to distinguish between the case where the oracle is instantiated with the 0 or with the 1. And now we essentially have something intermediate, where the oracle just responds by encrypting a random message instead of what the adversary queries. And then we can define a bunch of hybrid games, LI-RI, which answer for the first I queries by encrypting just a random message. And for all the remaining queries, they encrypt the left or the right message, depending on the game LI and RI. And whenever the adversary makes a repeating query, it will result in the repeating response the first time this query was made. Now for these games, we have essentially that this game L0 corresponds to the case here on the left, where always the left message is encrypted, R0 to the case where always the right message is encrypted. And the 2 games LQ star and RQ star correspond to the case here in the middle, and they are essentially the same. And with this, we can then do the 2 hybrid arguments, one over the LI games and another one over the RQ games, which then ultimately show that we can simplify this security notion to restrict the adversary to just a single challenge query. to conclude, so the one thing I did not show in this presentation is we further show that many schemes are actually susceptible to these resetting attacks by showing that they are insecure in this security notion. And the part I did talk about is that we show that security against a single challenge also applies security against multiple challenges in case of these resetting attacks. For this, we showed that the issue of the original proof approach and that this does not work. And we then give the alternative proof for the claim. This concludes my presentation. Thank you very much.
Thank you. Do we have any questions for the speaker?
I don't see any on the Zoom chat window. Ramanujam, anything from Julep?
Maybe I can ask a question here.
Please go ahead.
Yeah, so this notion of resettable security, did you explore any relation or is there an existing literature of its relation with other notions? For example, there are these notions called like related randomness or related key attacks, bad randomness.
Yeah, so the related randomness, this is essentially the paper by Patterson, Schult, and Seborn. This is an extension of this notion. And so here it was the case, there's this fixed randomness, which is used to encrypt. And in this related randomness setting, there's also that the adversary also specifies a function. And then this function is applied to this R star, and whatever the output is, this is then the actual randomness for encryption.
I see. So this is a specific case of related randomness. I got it.
And yeah, for bad randomness, this is a different case. I mean, there are the cases where you can argue that the randomness might have not enough entropy, but here it's the case that you still have the randomness is good,
but they just repeat it.
Yeah, the issue is you repeat it, and still it's unknown to the adversary.
Got it. Okay. Thanks.
Any other questions? It seems someone is trying to ask a question, but he's on mute. No. Okay. So since we have a few minutes here, would you like to elaborate on the first point on your summary slide? Like what kind of schemes are susceptible to resetting attacks?
So along with the notion, Jack showed that it's strictly stronger than in CPA by showing that the hybrid encryption scheme using a one-time pad as the underlying symmetric encryption scheme is insecure. And essentially it's because the randomness derived from the one-time pad key is derived from the randomness, so you will reuse the one-time pad key. So after one query, you learn this key, and then you can decrypt whatever you like. And we extend this and show that any instantiation of the one-time pad key of the hybrid encryption scheme is insecure, because you can just focus on because you will reuse the same symmetric key, and then you basically have the part that actually encrypts the message using the symmetric key. This will always be the same for many for the messages.
Thank you.
You can use a query for the learning oracle with a different public key, but this only affects the one part of the ciphertext, but not the actual part which encrypts the message.
Thank you.
Ramanujam has a quick question. Can you unmute? We weren't able to hear you. Okay. Maybe there's some difficulty unmuting, but the question is, when you fix the original proof, is the original bound affected?
We have so the original claim was that we have a factor of Q, and in our case, well, depending on the repeating curves, we have this non-repeating curves, which might be less than Q. But let's stick for the case that is still Q, and then we only get an additional factor of 2 due to the 2 hybrid arguments instead of 1.
Okay, sounds good. Okay. Any other questions? Okay, thanks. I don't think there are any other questions.
So I guess we are at the end of the session now. And are the speakers going to be around for a little while? If somebody has any question, maybe they can message the speakers.
So request the speakers to track the Zulip chat. There could be questions, if any.
There aren't any right now, but yeah, maybe there will be in some time.
Okay, so thank you, Bhavana, Shashank, and Ramanujam for chairing this session. So we'll take a quick 9-minute break and come back for the next session.
Thank you to all the speakers. Thank you.
Thank you. Bye.
Bye.
Thank you.
Thank you. Bye.